Okay, let's start. The first lecturer is Professor Nathan Berkovits from ICTP and the school in Brazil and the UNESP, and he is going to give us a set of lectures about supersymmetry and supergravity.
Thank you. So let me start by thanking the organizers. So Hugo, of course, has done 90% of the work. We've essentially just been telling him how we did it in the past, but every time is a new time, and I think the last one we had was 4 years ago, so probably none of you were present in the last one. So, of course, the background is different for all the different students. So the idea is that you have to ask questions and you have to interact, because otherwise the lecturer doesn't know. I mean, I can't just repeat what we've done in the last schools, because every time is different. So please ask questions, interrupt me. I think there'll be a discussion session later, but don't save questions for the discussion session. Okay, ask me now. Okay, so in all the other schools, I think these lectures were given by SAFE, run by Diane, who couldn't come this time. But I'm going to use his lecture notes. So I will say a few things different, but I'm essentially going to follow his lecture. So the lectures he gave in Bariloche are on the web page of Bariloche. So I'll give you that reference. So at least you know. A little bit longer, but so if you can't find it, just Google Latin American String School, Bariloche. So the outline that I will follow is slightly different from his, but the first lecture will be about spinors. So I will assume that you're familiar with the Lorentz group, but not much more. Because we're going to have to do spinors in different dimensions. So although many of you have probably seen spinors in 4 dimensions, maybe you haven't seen in other dimensions. So the first thing I'm going to do is discuss spinors, which are representations of this. This would be in Euclidean space in dimension 2n. So this is in even dimensions. Then we'll discuss in odd dimensions. Then finally we'll discuss generalizations to Minkowski space. So this is all Euclidean space because there's no time-like signature in this special orthogonal group. So we're going to discuss then Minkowski space. And then we'll discuss the reality properties of spinors in these different dimensions. So this is, of course, even space-time dimension, odd space-time dimension. And depending on the dimension, you have, of course, different dimensional representations, but you also have the representations can be real, pseudo-real, or complex. So it's important to understand these spinor representations if we want to discuss supersymmetry. So this will be lecture 1. And then lecture 2 will be supersymmetry. Of course, the one thing I should say from the beginning, when I say spinor, I mean a representation of the Lorentz group. It's not necessarily a fermion. Although for a physical for a state to be physical and to be a spin-order representation of the Lorentz group, it has to be fermionic. But sometimes people get confused about the language. So a fermion is something which is anti-commuting, which is a spinor as a representation of the Lorentz group. So of course you could have a boson, which is a spin-order representation, and you can also have a fermion, which is in, for example, a scalar representation. But they would not be physical, they would be ghosts. Okay, so the next subject, which will be tomorrow, will be supersymmetry. So I'll first discuss what the algebra is. And then certain properties that you can deduce from the algebra. So of course, the motivation for studying supersymmetric systems is essentially because of their properties. So they have better finiteness properties. They also have interesting mathematical properties depending on the dimension. And they're essentially interesting systems to study. And of course, superstring theory is one of those interesting systems. And now SAFE, differently from the lectures in these notes, SAFE started with the highest dimension and then he came down. I suspect it's more pedagogical to start with the simplest case and then go to the higher dimension. So we'll start with d equals 1, which is sometimes called supersymmetric quantum mechanics, or in our case, I'll think of it as the spinning particle. So I'll explain this, of course, tomorrow. And then when we go to d equals 2, that will be relevant for what's called the Ramon-Never-Schwarz formulation of the string. It's also called the spinning string. So this will tie in with the lectures of Carmen Núñez. So again, we can study this algebra in any dimension. So this, of course, is an odd dimension. It refers to SO2n plus 1. This is an even dimension. And then in the third lecture, we'll start to discuss higher dimensional supersymmetry. So we'll discuss four-dimensional supersymmetry. So SUSY is, of course, shorthand for supersymmetry. And this is, of course, relevant for people who are trying to understand supersymmetry as an extension of the standard model of particle physics. So that's, of course, one of the motivations for studying supersymmetry, but it's not the motivation that we're going to use here, which is more related to the superstring. But then there are higher dimensional generalizations of this, which are relevant for the superstring, which is d equals 10. And for membranes, we have d equals 11. And I will also discuss in this lecture how to find the representations of supersymmetry in any dimension. So we'll see, for example, that this is the largest dimension you can have in which you only have one graviton. That's 11 dimensions. So that will be the subject of the third lecture. And in the fourth lecture, we'll discuss extended supersymmetry, which is when you have more than just a minimal amount of supersymmetry in these dimensions. And the best way to, a nice way to understand these is by starting with minimal supersymmetry in a higher dimension and then doing dimensional reduction. So we'll say something about Kaluza-Klein. Dimensional reduction. And we'll discuss, for example, you can reduce this to 10 dimensions and get supersymmetric systems with twice as much supersymmetry as this case. So this will be super-Yang-Mills. And you can get supergravity theories in 10 dimensions by eventually reducing this case, and we have type 2a and type 2b. Equals 10 supergravity. And then if you go further down, you can get 4 dimensions. You can get either n equals 8, equals 4 supergravity if you start with all the supersymmetries, or we can also get n equals 4, d equals 4 super-Yang-Mills. have half of the maximal supersymmetry. And these are relevant, for example, for this ADS-CFT correspondence. And then we'll also discuss the idea of central charges. You have, this would be 32, 16, or 8 supersymmetry. Okay, so these are the topics which I hope to be able to discuss. If there's some topic that is missing, people want me to discuss, maybe you can tell me in a discussion session, and I can try to.
Excuse me, can you repeat the last? Because I cannot see.
Yeah,
Okay.
even better, let me move the whiteboard.
Thank you very much. Thank you.
Can you see now? Okay, are there any comments or questions? Okay, so that's the plan of the lecture. And today it's going to be mostly mathematics. We're going to discuss spinors. But it's crucial to understand these spinoidal representations, otherwise it's just going to be words. You're not going to be able to do anything by yourself if you don't understand a spinoidal representation. So it's a little bit dangerous when you give a mathematical talk that at the beginning everything is easy, so everybody, I do the same thing, they think I know this, I'm going to do something else. So if you already know how to define the real and pseudo-real and complex, you already know this part here, then maybe you can do something else. But if you don't know these different representations here, then you should pay attention from the beginning, because it's going to be difficult to understand what I do in the end unless you follow the notation from the beginning. Okay, so we want to start with the Lorentz group. So the Lorentz group is given by a generator. So if we were doing a Minkowski space, it would go from 0 to t minus 1. And t is the dimension of space-time, and it satisfies a certain algebra. Now, I'm not going to get the signs right, but I'll write something down. Then one of the exercises will be checking it. Okay, there'll be some other. So this is the Minkowski metric. But of course, we can do this also in Euclidean space, where this just becomes delta AB and delta BC. So these, of course, are also the generators of SOD, if I'm doing the Lorentz group. So in that case, it would be 1, 2, 3. And this is always antisymmetric. So probably you've seen this in 4 dimensions, but maybe you've seen it in any dimension. But this is essentially the Lie algebra of SON, or SOD. And now I'm going to split it up depending if the dimension is even or odd. So let's suppose the dimension is even. So this is equal to 2n. And now I want to find representations of this. So of course everybody knows, I think, that there's a vector representation which has d components. We know how it acts you hit with the Lorentz group. So MAT. Acting on some vector, something like delta DC. So I'm not careful with coefficients, so I'm not swearing by these coefficients. But these are okay, but there are other representations, and another representation is the spinorial representation that we'll discuss today. Of course, a scalar representation transforms trivially. So the way to construct this, the nice way to construct the spinorial representation is using Clifford algebras. So I'm going to suppose that there exists some matrix here. So I have D of these matrices, which
Is it a
says,
metric or a connection?
please,
Is it a metric or a connection?
I haven't a metric or a connection. This is a matrix.
Okay.
So I use the letter gamma, which sometimes people use for connection, but I'm using the notation of safe. So that's why I use the letter gamma.
Okay,
But
thank you.
it's a matrix.
Yeah.
So it's a capital gamma, which is why it's probably safe to use that notation. This is the Greek letter for gamma, is that right? Capital
Yes.
gamma. And this means the anticommutator. So those kinds of questions are excellent, okay? Because he asked the question, but maybe 3 or 4 of you had the same question. So please don't hesitate to it. So this is going to be 2 delta AB. Now, of course, in Minkowski space, this would be 8 AB, but we're starting in Euclidean space. So let me just remind you. Okay, so the first thing what you can show is that if these gammas satisfy this algebra, then if I define sigma AB be equal to be 1/4, not the anticommutator, but the commutator. In other words, this is antisymmetric in A and B, so of course it's the commutator here, that this sigma AB satisfies this relation. Of course, with sigma substituted for m here. Yes, thank you. I'm going to put delta here just a Now, in this case, as before, if I had called this eta, then of course it would be eta. So one of the exercises is to compute this dot dot dot. Of course, everything follows. Okay, what that means is that you can now find a representation by exponentiating this sigma, and that's how the SO2n transformations act on the spinorial representation. So what we're going to do is we're going to exponentiate it. All these parameters, A, this one. these would be the parameters of the SO2n transformation. And since, of course, this is some matrix, the exponential is, of course, also a matrix. And this matrix is going to act on the representation. Okay, and that's going to be the spinorial representation. And, of course, depending on the dimension of these matrices, which is the same, that will tell you the dimension of the spinorial representation. Okay, so now we're going to understand how to construct these matrices. Okay, and that will automatically tell us what the spinorial representation is. Okay, so just curiosity, how many people have seen this before? Okay, good. Okay, so now we're going to build up the representations. And for SO2n, the way we're going to do it is going to split these 2n matrices, because A goes from 1 to 2n, into n complex pairs. So we're going to have an index I, which goes from 1 to n, not from 1 to d. This I is the square root of -1. That's only now, I'm going to change a little bit the notation from, say if I'm going to call this B plus and this B minus. Now it's trivial to use this relation here to show that these B's satisfy because you get contribution from here and also contribution from here. And of course, Bi plus with Bij plus is equal 0, and Bi minus with Bj minus is equal 0. So these Bi plus and Bi minus, you can think of them as acting as creation and annihilation operators. And so if we think of this as a creation operator and this is an annihilation operator, then we start with a state which is annihilated by all the annihilation operators. You can think of it as a ground state. And safe called the ground state 0. I'm going to use a slightly different notation, which I think is more transparent. I'm going to call it the state minus, minus, minus. So you have n of these. So remember, these Bi's, I goes from 1 to n, so this, if B1, for example, acts on this one, B2 would act on this one, B3 would act on this one, etc. So this notation here implies that this state here is annihilated by all the B minuses. Bi minus acting on the state minus, minus, minus. For every I. But what about the B pluses? Well, those, you think of them as creation operators, they don't annihilate the state. And they will just flip the sign of the I minus sign. So for example, B1 plus acting on minus, minus, minus is of course equal to plus, minus, minus. And etc. So for example, Bn plus would act on the last one. Notation clear? Yes?
Do you have not working in any special image. I mean, when the Lorentz does these gamma matrices transform.
Okay, so these are matrices. So the matrices are just things like 0, 1, 1, 0, like the Pauli matrices that maybe you have seen. They don't transform, they're just matrices. So the spinors transform. For example, they will transform by, if you do a Lorentz transformation on this, the Lorentz transformation will be generated by this object here. And these sigmas are matrices constructed from these gammas, which will act on these. So these objects will transform. But the matrices don't transform. The matrices are just matrices. Is it clear?
What is theta?
Sorry?
What is theta?
Theta is a parameter. So if you do an SON, an SOD transformation, you have d times d minus 1 over 2 parameters depending on the axis where you do the rotation. And these are just the parameters of the rotation.
Last part, when you describe the VI as annihilation and creation operator,
Yes?
this, when you change minus to plus, it means that this just have two states or it's just annotation?
No, so later we're going to count the number of states, and indeed, the number of states is just you have a plus or minus choice here, plus or minus here. So in fact, since you asked the question, let's count the number of states. So of course, you can act with the pluses, and you can raise all of these to minuses, but eventually, if you act with all the B pluses, that's right. And then if you hit with more B pluses, you get 0. So now we can count the number of states. So who knows the number of states?
2 at power n.
Yeah. So you have 2 to the n states. Why? Because each slot here can either be plus or minus, and there are n slots, so you have 2 to the n states. So this is the representation of the spinor of SO2n. Now, I haven't told you yet if this representation is reducible or not. So what does reducible mean? Reducible means that, of course, the Lorentz transformations are going to mix these together. But it's not obvious that the Lorentz transformations are going to mix all of these together. Maybe it mixes them in 2 separate groups. And in fact, what we'll see in a few minutes is that, in fact, this splits up into 2 different groups, which don't mix under Lorentz transformation. Okay, before I talk about that, are there any questions? Okay, so in fact, I should probably put the exercises over here. So exercise 1 was to show that so this is when exercise 2 is a little bit more subtle, but what I've told you is how the gamma matrices act on these states, right? More precisely, I've told you how the B's act on these states. And if you know how the B's act on these states, you know how the gammas act on these states. Because gamma I is just the real part of BI. So I want you to construct matrices. Gamma. Let's do it when n equals 1 and n equals 2. So if you know how the matrices act on these states, you just use these states as a basis And there's your matrix. Okay? So essentially, I've told you it, but I've told you it in a slightly abstract notation. So construct these matrices when n equals 1 and n equals 2. And if you're brave, try to do it for all n. Doing it for all n, you will have to take direct products of matrices. But okay, so that's exercise. Any questions? Okay, so now as I told you, we want to decide if these states are reducible or not. So one thing we can see immediately is that they split up into two separate groups, which is related to something called chirality. So one thing you can see immediately, I'll say it in words and then I'll say it in formula, is that this object here always involves an even number of gammas. Because if you exponentiate something, obviously it either has 0 gammas, 2 gammas, 4 gammas. You'll never get a term here with just 1 gamma. Now if you have 2 gammas, each b changes 1 sign. Right? If you have an even number of gammas, you also have an even number of b's. That means you always have to change 2 signs. You can never just change 1 sign. So for example, to go from this state to this state, I changed 1 sign, right? Because I acted with just 1 b. If I act with 2 b's, I will always change 2 numbers, 2 signs. Or I won't change any sign. But I'll never change an odd number of signs. Now what this means is that the number of plus signs if it's even, it will always stay even. If it's odd, it will always stay odd. These two states, they're of course, because they're 2 to the n of here, they're 2 to the n minus 1 of these. The n minus 1 of these. These representations don't mix. They have different chirality. That's the way to distinguish them. And the object that measures chirality is called gamma 2n plus 1, or general gamma d plus 1. So this object is defined to be the product of all the gammas. Now, conventionally, this is defined such that gamma n, this object here, squared, this is a definition. So that the square of it is defined to be plus 1, I think. I want to make sure I use the same convention. Right. Now, using the properties of gamma, you can immediately compute the square, right? Because gamma 1 squared is 1, gamma 2 squared is 1, gamma 3 squared. So you might think this square is 1, but that's not true, because in order to, if you take the square of this, you have to pull this gamma 1 all the way through to hit this in order to get gamma 1. So the square of this is actually not always 1. It depends on the dimension. And if you want it to be 1, you have to put in a prefactor here, which is I to some power. Okay, where alpha will depend on n. So that's exercise 3. Find alpha. Gamma such that gamma 2n plus 1 squared. Okay, so it's not a difficult exercise, but you have to do a computation. Okay, any questions? Okay, now the claim is, well, the claim is that this object here, because it squares 1, you can choose a representation such that it divides up into matrix of this form, where this is a 2 to the n minus 1 dimensional identity. Okay, or minus identity. So although the square of the matrix is 1, the matrix itself is not the identity. And in fact, it cannot be the identity because you can check that this matrix here has the property that it anti-commutes with all the other ones. So this follows directly from just the fact that the gamma A is anti-commute. So it cannot be the identity because the identity would not anti-commute, it would commute with all the matrices. So in this representation that I chose here, the gamma A's are all off diagonal. So let me call this small. Where this again is a 2 to the n minus 1 dimensional matrix. And it's easy to see that this anti-commutes. So why is this off diagonal? Well, in this representation, remember the first 2 to the n minus 1s are even number plus signs. And the next 2 to the n minus 1 are odd number plus signs. And because these gamma matrices always take an even number to an odd number, or an odd number to an even number, you know that they have to be off diagonal in this representation. So this is what's called the Weyl representation. This is
I have a
what.
question.
Sorry?
A question. The fact that this gamma A are of diagonal is a consequence of the gamma 2 plus 1 is of diagonal?
It's a choice of representation.
It's a choice.
So once I've chosen my representation such that the first 2 to the n minus 1s are one chirality, and the other 2 to the n minus 1 are the other chirality, then that fixes me in this representation. And in this representation, this matrix here is, of course, just 1, 0, 0, minus 1.
One question. The way you have written gamma A
Yes?
looks like it's always a symmetric matrix, but it's not the case.
I haven't told you what the sigma A's are yet. So it's not obvious that it's symmetric.
But if sigma A is the same in the two blocks.
That's right.
All right.
I have to be careful. This has to be Hermitian. So, so it's not quite true what I said. If this is, for example, imaginary, then this should be minus it. So this is going to be the Hermitian constant. Any other questions? Okay, so this is essentially sorry, is there a question?
No, somebody talked.
Okay, so this is a description of the SO2N. And we've seen that any spinor can be written in terms of these 2 to the n states. And the 2 to the n states split into irreducible representation. so this is SO2n. This is essentially the simplest case. Now we're going to do SO2n plus 1.
Can I ask a question? Isn't there something funny in that in order to define the representations, you need to use something which is outside of the group, which mixes two different representations?
You're talking about
The gammas.
the gammas.
Why do I need something which is not on the algebra to define the representations of the algebra?
I think it's a convenient tool. So whenever you have a chiral representation, of course, you also have an anti-chiral representation. So you're correct in the sense that you don't really need to have matrices which are 2 to the n by 2 to the n. You really only need these matrices. So these matrices are 2 to the n minus 1 times 2 to the n minus 1. So in order to define spinors, you really only need these. Okay? I could have started with these, but then it's a little bit, we'll see when we do the 2 to the, when we do SO2n plus 1, we will really need the, well, it will be convenient to have these.
But I'm adding something, you know, like a discrete
So you're right,
idea.
these are enough. Everything can be built out of these sigma a's. So in that sense, these are the building blocks. So sometimes people use the notation, this is a gamma matrix and this is a Pauli matrix. Any other? Okay, so now we want to do SO2n plus 1. So fortunately, we have all the ingredients already on the board. Because remember, the starting point is we had gamma A, and we defined sigma AB equals 1/2 gamma A. Just 1/4 of
1/4.
1/4. And of course, this did not care if I was doing even or odd. A went from 1 to D. So if D is odd, it just means I need to have instead of, so if this is 2n plus 1, it just means instead of having 2n of these gammas, I need to have 2n plus 1. But in fact, we already found this matrix here, which satisfies precisely the properties we wanted. So the 2n plus 1 gamma matrices are going to be obtained just by starting with the 2n gamma matrices we constructed before, and including one more, which is this. So we see that the dimensional of this representation is still 2 to the n, because we have the 2 to the n states. However, in this case, we cannot reduce it to something which has 2 to the n minus 1. So there's no definition of chiral or anti-chiral representations in this case. We have to include all of them. We have to include here we have n. Remember, the dimension is 2n plus 1. So now, so the reason why we have to include all of them, just to be clear, is because we could, of course, if we were strict to Lorentz transformations, which only involve the first 2n indices, or SO2n transformations, which is a subgroup of SO2n plus 1, then of course it would preserve the property that even number of plus signs only go to even number of plus. But as soon as we include SO2n plus 1 transformation involving the last one, so remember this thing splits up into the gamma i's, gamma I plus n, and then the last one, which is gamma 2n plus 1. product of all the other ones. This one does not change the number of pluses or minuses, right? It just gives me +1 or -1. It does not change doesn't do anything to these plus or minus things. So as soon as I consider, for example, gamma, the last one, let's say I 2n plus 1, this is a SO2n plus 1 transformation, which is of course equal to 1/2 gamma I, gamma 2n plus 1. This one changes the number of plus or minus signs just by 1, because this one changes, this one doesn't. So that's why once I include SO2n plus 1 transformations, I'm forced to include all of them. Because the SO2n plus 1 transformations, some of them change the number of plus and minus signs by an odd number of plus signs. So the minimum dimensional representation is okay, so this is a summary of representations of SO2n and SO2n plus 1. So we found that just to summarize, so for SO2n, we have the representation splits up. You have 2 to the n elements. So these, of course, split up. 2 to the n minus 1 tiles. These are associated with an even number of plus signs. These are an odd number. This 2 to the n is, of course, plus and minus. Now when we do SO2n plus 1, what we've done is we've included now an additional gamma matrix. So we have gamma I. Think of them. Put them in the same combination as before. But now we have one more, which is this rotated? Then the last one is gamma 2n plus 1. Just the product. And here you have 2 to the n. Same notation as this, but now there's no way to separate them. Okay, so this, I hope this point was made. So is there anybody who has any questions about this? Okay, so this, of course, now allows me to do spinors in any dimension. And now the last thing I want to discuss is the reality properties of this representation. So the first thing to decide is if this representation here, let's start with SO2n. If this is real or complex. So what does real or complex mean? Real means that if I take the complex conjugate of this representation, do I get the same representation? Or does it transform me into this representation? So it will turn out in certain dimensions, this is a real representation, which means the smallest irreducible representation is 2n minus 1, 2 to the n minus 1 real elements. Whereas in other dimensions, the smallest representation is not 2 to the n minus 1 real, because this turns out cannot be real. The complex conjugate has to be this. So in that case, you have 2 to the n minus 1 complex component, which is of course equal to 2 to the n real. So the real dimension, this is not enough yet to determine the real dimension. We have to figure out if the dimension, if the representation is real or complex. Okay, any questions? Okay, so let's do that. So it's not so difficult. So all you have to remember that when I'm in Euclidean space, this I take the complex conjugate of this, I get the opposite sign. Because I should have stressed this, these are Hermitian matrices. So that means that BI plus, if you take the complex conjugate, is BI minus. So what that means is if I start with this state, and I take the complex conjugate, well, obviously, if it started out being a state which is annihilated by all the B minuses, and I take the complex conjugate, well, now it's annihilated by all the BI pluses. So the complex conjugate of this state has to be this state. Is that clear?
One question. How do we know the gamma i's are real matrices? Shouldn't that complex conjugate be a Hermitian conjugate?
So in SO2N, I'm telling you that these gamma i's are Hermitian. How do I know that they're Hermitian? So the sigmas that I defined earlier, sigma AB, has to be anti-Hermitian for them to be in the Lie algebra of SO2N. So I want these gammas to be Hermitian matrices. So when I take the complex conjugate, or Hermitian conjugate, I'm going to get the same thing with just the So just to confirm, we're still in Euclidean space. When we go to Minkowski space, things will change a little bit. I mean, I have not yet discussed the Lorentzian signature of Minkowski. Okay, so this is the complex conjugate of this. Now, if we want this to be a real representation, what we need is that when we take the complex conjugate, an even number of plus signs goes to an even number of plus signs. Well, that's going to depend on the dimension here, because here, obviously, we have 0 plus signs, and here we have n plus signs. So if n is even, then we've gone from an even number of plus signs to an even number of plus signs. So when n is even, then the complex conjugate of a chiral representation is still a chiral representation. So there's a possibility that this representation is real. Now I'll put a question mark here because we'll see this something else called a pseudo-real representation, which will make life a little bit more complicated. But at least there's a possibility that there are 2 to the n minus real. On the other hand, if n is odd, you're stuck. There's no way that this can be real because the complex conjugate has to be anti-chiral. So when n is odd, we know we have complex components. So the minimum number of real components is 2 to the n. So for example, n equals 1 corresponds to d equals 2. If d equals 2, this thing has to be complex. Has to be related to the fact that the superstring or the spinning string, we work in Euclidean space on the world sheet, the number of spinners has to be at least 2. Okay, on the other hand, when n is even, we have this possibility. Any questions?
Yes. So I shouldn't be minus the opposite in the other side of the equation.
Here?
Here.
If they are minus.
Minus, that's what I wrote, minus.
Okay.
Sorry. Any other questions?
Yeah, can you repeat the logic, please, on how being n even you can say, okay, so we have the possibility that
Okay,
the
good. Thank you for
components
the
are real.
question. So this object has 0 plus signs, right? This object has n plus signs. The complex conjugate of this is this. At least it's proportional to this. So that's going to be related to this subtlety that I'll discuss later. So we proved that the complex conjugate of this is annihilated by all the bi pluses. So it has to be proportional to this. But I haven't told you the proportionality constant. When the proportionality constant is 1, then you say that this is the complex conjugate of this. Now, if this is the complex conjugate of this, and this has 0 plus signs, then this side has an even number of plus signs. Now, if you want this representation to be real when n is even, then obviously this has to be even. So what I'm trying to ask is if this representation here can be real. So if the complex conjugate of this representation has an odd number of plus signs, it can't be real. Because the complex conjugate of this gives you this. So it can only be real if the complex conjugate of the representation is the same representation. Which means it has to have an even number of plus signs. So that's only possible if n is even, because this has to have an even number of plus signs.
Thank you.
Any other questions? Okay, now the next level is pseudo-real. Okay? So I told you that this is actually proportional to this. Let's call it some constant. It turns out that this constant may have to be imaginary. So it may actually, there are no real representations. And let me give you, this is not so trivial to show, but let me try to give an argument. So let's suppose that n is 2, to give you a simple case. So we want to say that the complex conjugate of this is equal to plus plus. Now, using our notation here, this is equal to bi e1 plus e2 plus on minus minus. So let's suppose this is true. Then the complex conjugate of this is equal to this. So what I want to show is that this leads to a contradiction. And the contradiction is if we take the complex conjugate of this, we should get back to the original state. Okay, so plus plus. Now this is going to be equal to E1 minus E2 minus E1 plus. So we're doing the operation twice, but of course the second time we're doing it, we're changing plus to minus because we're taking the complex conjugate. We're doing the operation twice, but the second time we're doing it with the complex conjugate. So this doesn't work. So what I'll show you is that this leads to a contradiction. This would imply that minus minus double star is equal to minus minus.
Excuse me, but I do not understand very well. Why are you applying the A minus and B plus sign?
Yeah, let me say it again more carefully. So what I want to compute is this object. I want to take the complex conjugate twice.
Oh, okay, because you didn't put the star twice.
Yeah, here I put plus plus, so that's because
Okay.
so this is equal.
Okay. Yeah, thank you.
So consistency would imply that the complex conjugate twice of something has to be something itself. And now if the complex conjugate of minus minus is plus plus, then we can do this in two steps. First we do the first one, and we get this, and then we do it again. But this procedure, if we do it again, gives you this object here. And now we use the anti-commutation relations of B1 and B2 to see that actually this is not equal to minus minus. So this is equal to 1 minus, minus, 1 plus. Now you have to pull this through. So B2 minus annihilates this, but there's a non-trivial commutator when it goes through here. So you get minus. So we pulled it through once, then we pull it through again. That gives me a plus sign. I mean, it gives me a 1 because these two don't intercommute. This is equal to minus 1 plus. Or I pulled this through and used the fact that B2 minus times. And this, again, I pull that through and it gives me minus. So if I assume that this is the complex conjugate of this, and I do it twice, instead of getting the same state back, I get minus the state. That implies that the state is pseudo-real. Now, I could have done the same thing, but now suppose, so this was for n equals 2. Let's do now n equals 4. And I'll show you in that case, everything works nice. So for n equals 4, one state, no, 4. So we want this to be equal to plus 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 plus. Plus 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 is equal to B1 plus 2 plus 1 minus minus minus. Now you see you have more minus signs. You get one by pulling this through, you get another by pulling this through. So this one, when you compute it, what you'll find is that you get this equal to minus minus. So in the case when n is even, you may get either real or pseudo-real. So what we found first of all, if n is odd, that implies you have complex. There's no choice. You have 2n minus 1 complex. When n is even, there's a choice. Depending if n is equal to 2, 6, 10, I could have showed, it's easy to show that this pattern repeats if you change n by mod 4. So n is equal to mod 4. This implies pseudo-real. When n is 0 mod 4, implies it's real. So you have pseudo-real 2 to the n minus 1. What does pseudo-real mean? Pseudo-real means that you actually have a doubling of the number of states. So if you try to take the complex conjugate of this, it cannot be equal to plus plus. It has to be equal to a different object, which has the same obvious properties under the B's. It's annihilated by the Bi plus, but it can't be this one. It has to be a different one. Another way of saying what I'm saying is if you try to construct the gamma matrices, and you ask if the gamma matrices can be real or not. And what you'll find is that in this case here, you can find representations of the gamma matrices which are 2 to the n minus 1, 2 to the n minus 1 real matrices, but not in this case.
One question. How can we be sure that the pseudo-real representations cannot be put in a real form with a suitable choice of bases, the states?
Well, I think this argument here was independent of the basis.
Oh, but you could define that complex conjugate of minus minus to be e to the I alpha something times plus plus, and likewise for...
I'm sorry, so you're proposing, so this kind of question might be best for the discussion section, but let's see. Do you want to propose this is equal to e to the, let's call it I alpha times plus plus?
The complex conjugate of minus minus.
Right.
Yeah.
And then plus plus,
Equal to e at I times beta.
this would be e to the I beta,
I times beta.
a different
Yes.
times minus minus. And you would like to adjust alpha and beta such that this is consistent.
Well, I would like to know if it's possible.
So I think, if I look at this just naively, it looks like this would have to be minus this, is that not right? So if I take the complex conjugate of this, I have to get this one, right? So that means this would give me, it looks like these two have to be the same. So let me do the argument. This thing here, if I take the complex conjugate of this, it implies that minus minus is equal to e to the minus I alpha plus plus star, right? And now I just move the e to the I alpha to the other side. So it looks like this implies this.
Okay.
And now it looks like this would imply that minus minus star star. So I'm going to do it twice. So I take the star of this, it gives me e to the minus I alpha times plus plus star. But I already decided plus plus star is equal to this. So I'm back to the same contradiction. It didn't seem to help.
Okay. Thanks. Thank you.
Any other questions? Okay, so the last thing we're going to do today is Minkowski space. So if you've understood this for Euclidean space, it's trivial to do Minkowski space. The only thing you have to do is multiply one of the gammas times I. So now, I'm not going to approximate Minkowski space. I'm just going to explain how to go from one to the other. So what that means is that gamma 0 squared is no longer 1, it's minus 1. Okay? Because remember, gamma A, gamma B is always equal to 2 e to AP. So if we're working with time-like signature, then gamma 0 squared is minus 1. So gamma 0 cannot be Hermitian. It has to be anti-Hermitian. Okay, so now when we construct the BIs, let's do it first for SO2N. Again, we do the same thing as before. BI plus is equal to gamma. Let me start with 0 now, just instead of starting with 1. So we start with I. Probably I should have done it the other way. Let's say the time-like signature is the last one. Just in this notation. Sorry for the change in notation, but let's say the time-like signature is the last one. one of these EIs, because this thing is anti-Hermitian, if you want this object here to be the complex conjugate of this, the last one, so this is for I equals 1 to n minus 1. Last one, which we'll call Bn, we're going to do without the I.
Just one question.
Yes.
You said that gamma 2n has to be anti-Hermitian.
Yes.
This is with respect, I suppose, with respect to this canonical plus-minus basis with some inner product.
No, I think it's independent of the basis. If you do a basis change, something is Hermitian, I think it is.
No, it is not. Hermeticity is a basis-dependent concept. And it
Hermeticity is not the basis. Did you say it is or is not?
Hermeticity is a basis-dependent concept.
Okay, I believe you. So, let me think about it. I'll try to give you an answer to this question. But certainly, if the square of the object is -1, let me say it for discussion section so I can say it wrong. Okay, so the last B's, if I want to keep the same properties as before, I will need to remove the I here, right? Because I want the property to be always to have the EI, J minus, is equal to whatever, 2 delta theta, delta I. So if I put an I here, I would get the wrong answer because I will get another minus sign, right, from this property here. So my last B, the one when I'm working Lorentzian signature, should not have the I. So what I want to say is that if I consider this state in Lorentzian signature, so this state is defined in the same way as before. It's annihilated by all the B minuses. But now when I take the complex conjugates, because of this property here, that there's no I here, the complex conjugate will not flip the last sign. Conjugate of this is equal to plus, plus, plus. But the last one will stay minus. So that's going to change all of these concepts of chiral versus anti-chiral, etc. So let's see how it changes. So is it clear why the complex conjugation properties have changed? So let's reanalyze this question here. So we still have the properties of chiral versus anti-chiral. We still have even number of pluses versus an odd number of pluses, so that never changes. We always have the representation split into either chiral or anti-chiral, but now the reality properties of these will be different. So we can do the same question here. Suppose we start with something with all minuses, and we take the complex conjugate. I just told you this is going to be equal to plus, plus. And the last one stays minus. So this has 0 plus signs. But now in Minkowski space, this has n minus 1 plus signs. Right? Because the last one stayed minus. So now in Minkowski space, in order to get the possibility that this representation is real, instead of n being even, n has to be odd. So n odd now implies that you can have 2 to the n minus 1 real. Again, we will have to work a little bit to decide if it's pseudo-real or real. But if n is even, we know we need to have 2 to the n minus 1 complex. Okay, so this is something you have to remember, because when you're distinguishing Euclidean from Minkowski, or in fact any signature, you have to work out which of these b's are real and which have an I and which do not. And that's going to determine if the representation can be real or complex. Now, if you work out the same...
Why isn't the absence of an I compensated by having an anti-Hermitian?
Good question. Anything else?
It is still true that the conjugate of the annihilation operator is the creation operator. Because you pick up a sign.
But these are not complex conjugates anymore.
Because gamma 2n is anti, picks up a sign when you do Hermitian conjugation. No?
Yeah, but I'm doing...
So that's the reason for taking out the I thought.
Let me answer this in the discussion session.
Okay.
I agree with you, it's confusing, but I'm just taking the complex conjugate, I'm not taking the transpose. So let me think about it, but I am sure that this is the complex, that this is, when you take the complex conjugate, this goes back to itself. But let me try to answer your question about Hermitian versus anti-Hermitian. Okay, so again, we're going to have a split into real and pseudo-real, and you can do the same analysis as before. So what you'll find is that it's pseudo-real. When n is equal to real, when n is equal to, let's see, I'll get it right. 1 plus 1. And it's pseudo-real and n is 3 1. So this would be, for example, if n is 1, that means the dimension is 2. So in 2 dimensions, you have real representation. The next one would be n equals 5, which would be d equals 10. So in d equals 10, you also have real, so 2 to the n minus 1 real representation. So for example, in 10 dimensions, the minimum representation has 2 to the 5 minus 1, 16 real components. Where if n is even, you always get these 2 to the n minus 1. And you can do the analysis precisely the same as we did in the Euclidean space.
I have a small question. Before we had SO2n, so it is now SO1
Yes, thank you.
1 minus 1.
Okay, and now if you want to do, finally, the case where you have odd dimension, so t is equal to 2n plus 1. So in this case, we're doing SO2n1. We do precisely the same trick as before. We construct the gamma matrix. We'll call gamma, gamma. There's again going to be I to the alpha times gamma 1. Alpha will be different because the gamma matrix properties are different because of this. But again, you can easily compute alpha such that this object squared is equal to 1. And now you can combine these with the other gamma matrices to construct the coherence generators now for the full SO2n, 1 Leon. Okay, so that's essentially the discussion, the concepts that you're going to have to remember for the higher dimensional spinners. So just to review, so in Euclidean space, this is these are the properties of the spinners. So you have these violent and anti-violent representations if you're an even dimension. And depending on if d over 2 is even or odd, so n is d over 2, you can either get these complex representations or real or pseudo-real. And for the Minkowski space, I'll just summarize it here. So if n is odd, you can either get the real or pseudo-real in these cases, so when n is 1 plus mod 4, or 3 plus mod 4. And when it's even, because of this property here, you're forced to work with complex components. Okay, so in the next lectures, we're going to discuss specific cases. So as I said, we'll start with the lower dimensional cases. And then as we get more familiar with the supersymmetry, we'll go to the higher dimensional. Okay, so we still have some time, so let's, maybe I can start to answer some of those questions, but are there any other questions before I go back to the ones that I wasn't able to answer?
We have a different question. What's the distinction between pseudo-real and complex? Why are not the pseudo-real just called complex?
Okay, so in this case, let's go back to the Euclidean case. Okay, so SO2n, so what does complex mean? It means that if you take the complex conjugate as a representation, you get a different representation. So I'm more familiar with examples. So let's work in Minkowski space, just because that's probably the case which probably some of you are also more familiar. So let's say d equals 3, 1. So you do a 4-dimensional. So you can have spinners, use the letter chi. Remember, this representation, this would correspond to the choice plus plus, minus minus. This would correspond to the case plus minus, minus. So remember, there are 4 possible combinations. And now, if we're in Minkowski space, and you take the complex conjugate of this representation, remember the second index doesn't change, but the first index does. So the complex conjugate of this is this one, right? Vice versa. Complex conjugate of this is this one. So if you take the complex conjugate, it changes the chirality, it changes the representation. Okay, so that's the definition of a representation which is complex. This is not pseudo-real. Okay, now if you go to d equals 5, 1, remember in Minkowski space, if you're in 1 plus mod, this is n is odd. Right, this is n even. Right, so this is the complex
So you want
case.
2,1.
Now I want to do the pseudo-real.
Oh, then.
So I want, so let's say n is equal to 3. N equals 3, that corresponds to d equals 5, 1. Okay, so we're going to do this case. Now in this case, this object here, alpha, 1 and 2 this case, instead of going from 1 and 2, it goes from 1 and 4 because you have these possible combinations. Plus, plus, plus. You have plus, minus, plus. Let's do it. I'm trying to write all the ones with an odd number of plus signs.
You repeat.
Yeah, 1 second. I'm just trying to do this. So these are the objects which have the same chirality, right? Because they have an odd number of plus signs. And then, of course, you can write the other 4. Have an even number of plus signs. So these are the 8 possibilities. Remember, you have 2 to the 3 possibilities. Here you have 2 to the 2. Now, in this case, a chiral spinner has 4 possible components. Okay, let's call it selection A. A equals 1 to 4. So this would be a spinner of one chirality. This would be a spinner of another chirality. If you take the complex conjugate of this spinner, you do not get this spinner. Because, for example, let's take the complex conjugate of this. The last plus stays the same. So the first 2, it's just going to take this. You might think it takes this to this. But it can't. The complex conjugate of this can't be this because of this contradiction. So what you need to do is you introduce 2 chiral spins. So let's call it chi A1 and chi A2. And what you find is that the complex conjugate of chi A1 is equal to chi A2. And the complex conjugate of chi A2 is equal to, I'm going to get this sign wrong. It might be, well, it's a convention if I put an I here or not. But okay, so if I want to get to the complex conjugate of the thing twice is equal to this, it has to be this. But my point is that it's not possible to define this to be equal to this. That's going to be a contradiction. You have to introduce twice as many. So the number of, these are spinners of the same chirality. So if you take complex conjugate, you don't get a different chirality, but you get a different spinner. You can't have the same spinner. So in this dimension, the minimum number of components is not 4 real, but 8 real. So that's the difference between pseudo-real and complex. It doesn't change the chirality, but it does change the spin.
So these 2 representations, in some sense, have different quantum numbers. They have different quantum numbers.
Okay, good. So
there is some.
Good. So let's ask. So first of all, we can ask for each of these individual representations, each of these individual components. These, of course, carry different charges under the Lorentz group. But now you ask me about how the chirality are measured. That's what you mean by quantum?
The two representations that are matched by complex conjugation?
Yeah. So if you did the chirality, so these 2 representations have different chirality.
Those are different representations of the Lorentz group.
Do you want to know what the you want to know how the quantum number, what
when I have
object measures?
The pseudo-real case,
yes?
I have a map between the same representations which have, are they the same representations of the Lorentz group?
These 2 transform identically under the Lorentz group. This one, they both transform this way under the Lorentz group. They do not mix under Lorentz transformation. They mix under complex conjugation. This cannot be real. You can't choose all 4 of these to be real. So that's how they're related, not by their Lorentz transformation. So this, under Lorentz transformations, this index does not transform. The only thing that transforms is this A. It just mixes these 4. But what you need is you need two sets of these. So let's call this 1 and 2. And under complex conjugation, this is equal to this. It's not equal to it. It's not doesn't match this.
So are you saying that we need two teeth
Two copies.
for getting the same result of the V equal to 3 period 1?
So, I'm not sure where you said d equals 3, but if you're doing the d equals 5, 1 case, you're asking about this case?
Yes.
So in this case, the minimal number of spinner components is not 4, it's 8. If you want all the components to be real, you need 8. You can't do it with 4. And the reason is because of this pseudo-real property. Another way to say it is that you can't choose these matrices here to be 4 by 4 real. There's no 4 by 4 real matrices that will transform these. So you need 8 by 8. There's no way to do it with 4 by 4 real matrices.
Does this also happen on the ones on the bottom?
Yes.
You have to have 2 copies.
That's right. You need 2 copies of these also.
So you have 2 copies of the ground state. And you also mentioned spin.
Yeah.
Is it like the same ground state but with different states?
So you need 2 copies of the ground state. You need 2 states which are both annihilated by all the B minuses. Call this 1 and 2. And the complex conjugate of this, okay, it won't be related to this, but it will be related to the plus 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 minus, which is also this.
But is it 2 degeneracy? Is it related to spin, or because you mentioned it before?
It's related to the complex conjugate properties. So I don't know what you mean, is it related to spin, but it's related to the fact that this cannot be, you cannot have just a single real representation. You need 2 in these certain dimensions. Okay, so this is not an easy concept to get right, but okay.
You said that we need 2, but when you add the operation of conjugate.
Yes.
But why do we need to add this operation?
Okay. There's another way of answering this, which is the usual way to say it, which may be satisfactory to you. It's not so satisfactory to me. Is you can ask, suppose you try to construct these Clifford algebra matrices, and you can ask the question in a different way. Can I construct these matrices such that all the elements are real? Okay, which satisfy this property, this Clifford algebra property. So you want this, the Clifford algebra to satisfy this property. And you can ask, what's the minimum dimension of this matrix where all the elements are real such that it satisfies this property? And you find again that in d equals 5, 1, you need 8 by 8, not 4 by 4. Okay? So that's another way of saying it. But okay, you had it. I don't know if that helps you, or I don't know if you want to re-say your question.
I don't get it. What you said?
Okay, I tried to give another explanation of what it means to be pseudo-real. Why in some cases you need to have this pseudo-real. It's related to the same thing I said before. I just tried to say it in a way which maybe is more familiar to people. But okay, what was your question? Can you say it again?
Why do we have to add this operation about conjugate?
Okay, so you want your components to be either real or complex. So if you want to restrict your component, you want to count how many real components do I have. So it may be, in order to define something to be real, you have to know that the complex conjugate is the same thing, right? So in this case, where it's pseudo-real, the complex conjugate cannot be the same thing. It has to be something else. So that's why we call it pseudo-real.
Why is the second explanation is not that satisfactory?
The one about the
yes.
Oh, it's because how do I prove to you that you can't construct
okay.
it? I don't know a proof. Okay? Whereas this one, I was able to give you a proof. That's the only reason.
So you have these 2 copies. What is the difference between them?
There's no difference. They both transform the same way, but they're not identical. You just need twice as many of them. You can't do it with just one. I don't know. Somebody, Is there some simple toy model that will make it more? So the simplest case in which this happens is, for example, if we're doing in Euclidean space, it's in 4 dimensions. If we're in Minkowski space, it's in 6 dimensions. So in 6 dimensions, you find that you need 2 copies of these 4 components.
And they are related because via this complex
That's right.
conjugate.
They're related by complex conjugation. Maybe the last question.
When you make this counting of the number of real or complex components, this is the number of components in the matrix or in the states?
In the states, the representation.
Okay, we could continue in the session of questions. So let's thanks for speaking.